Hello everyone, we are the BTech Acoustics Senior Design Group, and as Professor Perdue just said, our project is called Accelerometer Survivability Testing. My name is Megan Scribner, and my team members here are Eduardo Perez, Robert Lynn, Richard Cooler, and Aaron Williams.
Presentation outline. In this slide, we're going to talk about the contents of our presentation. It represents the research that we have done over the period of the project. If I can point your attention to the image, that is the Center of Innovation and Entrepreneurship. This is where we met our client, Dr. Rashad of BTech Acoustics. BTech Acoustics is a company firm that researches, develops, and manufactures transducers. BTech's transducers are used in a wide range of applications, and it's highly important for BTech to be able to test their transducers. If you look at the two images on the right over there, the top image is a barge test, and the bottom image is a mechanical shock test. The price, as you can see the price range between the two, and you can tell like they're very expensive, and like they can't be done too often because of how expensive they are. So BTech has tasked us with researching and designing a method that could test the physical survivability of the transducers before they are shipped off to be tested by the two tests for the military standard MIL-S-901D. I'm going to pass off the mic to Robert then for goals.
Thank you. Okay, so for accelerometers and their electrical components, sensitive sensors can measure a varying acceleration levels more precisely, while more robust sensors have a higher strength at the cost of that accuracy. So the objective of this project was to identify a test method to test the sensors. Along with the test method, we had to figure out the failure points in which components of the sensor, if they fail in the test, and also to collect the data in the test and analyze the data from the acceleration. On the right on the slides is an example sensor of an accelerometer. For those unfamiliar, an accelerometer works by the discs in the middle. They flex, and we use that with the transducer to measure the acceleration. This is a quick contribution slide. Although some of us focused more on research and design, and others more on computer-aided simulations, we all thoroughly helped each other go through all the steps to complete the project. So for our initial design and considerations, the first test that we looked at was pendulum test. Pendulums, of course, are a large mass at the end of a strong arm, and using gravity, we use it to swing down at the sample. An alternative design is the water hammer test. That would use a high velocity of a fluid through a pipe and a sudden valve shut-off to use the pressure surge from the fluid and use that pressure to potentially use on the sensor. The last test that we looked at was the Hopkinson bar test. The way that one works is the sensor is fixed onto one side of the bar and another bar strikes the middle bar from the other end. I'm going to hand it to Richie for process selection.
All right, so I will be discussing the design approach here. And so the main focus of the selections are to achieve adequate levels of acceleration and force while keeping the cost low and the accessibility of the setup as high as possible for the client and for the group. There are some setups that require certain specimen dimensions that we had to account for. And then after a number of preliminary calculations and design brainstorming, we came up with a final design. We decided to use the Hopkinson bar. That's because the force can be controlled very easily. It's incredibly accessible. There's a Hopkinson bar setup on campus currently. And it also requires little to no modification to use. So here I'm going to talk about the adapter. So the reason why the Hopkinson bar needs an adapter is because the Hopkinson bar itself is 1/2 inch in diameter, while the sensors can range from 1.5 to 2 inches in diameter. roughly. And the whole goal of the sensor, or the whole goal of the adapter, is to distribute the force more uniformly on the sensor itself, on the diameter of the sensor, and also it provides a method of mounting the sensor to the backplate. It kind of sandwiches it in between the backplate and the adapter, rather than using like an adhesive, so that we can swap and run tests quicker. So on the left here, that's our first iteration. It's size adapter 1. We used a conical, or not conical, we used a cylindrical design here. It ended up being too heavy at 800 grams, so we ended up going with a size adapter 2, which uses more of a step geometry, and that is what we went with henceforth. And then at the bottom right here, you can see the stainless steel adapter, backplate, and baseplate that we manufactured. Now I'm going to be discussing the test method. The top right figure here is kind of the best way of describing how we've been testing these sensors. So in the top left here is the gas gun that can vary between 15 to 40 psi, and that propels the striker bar here, and that hits the incident bar, sending an incident pulse along the Hopkinson bar through the adapter into the sensor and backplate, and then back with a reflected pulse. There are 2 strain gauges hooked up to a digital readout oscilloscope, and then the sensor itself is hooked up to a clever scope, which it's a branded oscilloscope that you can plug in to your laptop. And then the bottom figure here is an actual test setup that we have. You can see the adapter, and then the sensor, and then the backplate. And now I'll be showing a quick video of a preliminary run and then an actual experimental test. 3, 2, 1. And I will be handing it off to Megan, who's going to talk about the results.
Okay. So the main results that we were interested in collecting was voltage versus time data from the strain gauges on the Hopkinson bar, as well as from the sensors that we were testing directly. With the Hopkinson bar, we were able to use MATLAB code as well as certain equations that are representative of how a wave propagates through the bar during a stress impulse in order to further calculate force and acceleration data. As far as the sensors, there are certain equations that relate the voltage output measured from the sensor with the PZT geometry from within the sensor, and those relations can then be used to calculate the acceleration that the sensor was subjected to during testing. On the right, you can see voltage versus time data that we collected from the strain gauges, as well as from the sensor samples that we used during testing. The initial test runs that we had done were at a high PSI value on a number of sensors that had different substrate materials. These sensors failed, and then we identified what parts of the sensor were affected during failure. For the first one, with substrate material 1, it was the substrate that failed. On the second one, it was the different material of substrate. It was the PZT that failed. For sensor number 3, we went back to the same composition of sensor 1, but this time it was encased in neutrally buoyant syntactic foam, which is used in some of the oceanographic uses for BTech sensors, as well as when it is put into larger test coupons that is used. Being able to identify what parts of the sensor are failing at certain impact levels is important to be able to identify what sort of sensor compositions and materials best balance sensitivity with robustness. In terms of validation, we had one method for determining the Hopkinson bar, validating the data, and then another method for validating the data that we were collecting from the sensors. For the Hopkinson bar, we ran multiple tests at a particular PSI value, and we overlaid the voltage versus time data as seen up above, and looked at the magnitudes of the incident pulse, which is the first pulse that travels through the bar. You can see that the magnitudes are similar to the same, which helps to validate that when the compressed gas gun is set at a particular PSI level, that the same force is being delivered through the bar and to the sample that we are testing. For the sensor sample, we did multiple tests starting from a low PSI value to gradually higher PSI values, and in between each of these tests we would do an impedance analysis on the sensor. What the impedance analysis does is looks at the resonant frequency of the sensor. When there is external damage, such as when the substrate fails, it's easy to see that the sensor has failed. But if there's only PCT damage, you may not necessarily know that the sensor has failed in some capacity. So with the impedance analysis, if there is any damage to the PCT element, there will be a dip in the resonance frequency, and then you can tell if there has been some sort of damage or failure of the PCT element in between tests, and that just helps to better identify what force levels there is some sort of damage being done to the sensor. We did some additional analysis with the data that we had collected. Above, you can see that we have charted the max voltage output from the sensor, along with a numbering of tests that we did, each with increasing PSI value. From tests 1 through 5, you can see that there's sort of an increasing, almost linear trend, and then a big drop at test 6. We believe that this was due to user error, which we sort of validated with the graph below, which is a dual graphing of the maximum voltage output with the strain gauge voltage output. Both experience a very large dip at test 6. And so it's not just sensor failure here, the strain gauges are also measuring very low. So this was definitely, the machine was not delivering the force that we were expecting to. So that is why there's such a big dip in the sensor output. Moving forward from that in test 7, there was some recovery in terms of voltage output with additional increasing PSI, but it did not fully recover to the point where it did before. And after test 5, we had measured a slight dip in impedance, so we do believe there was some sort of PCT damage done after test 5, which didn't allow it to fully recover to the trend we had been seeing earlier. But we are able to identify a partial linear trend from tests 1 through 5 that we conducted. Now I'm going to pass it off to Aaron Williams for project outcomes and challenges.
So one of the main challenges we faced pretty much during the entirety of the project was just our communication between all the different various parties involved. So since we're working with many different people, everybody has different thoughts and opinions on how the project should go, where we should go continuing forward. And as Richard mentioned, we had a problem in our initial size adapter, so it was too heavy for the Hawkinson bar. So with the help of Paul Souza, we were able to machine a second iteration of that, which was much lighter with step geometry. And then for our first initial tests, we started with the maximum PSI for the gas gun, which, as Megan mentioned, caused sensor failure. And so since these sensors had failed upon impact, it actually skewed the data, so we weren't really able to get reliable data from those first few tests. We also had semi-limited testing availability due to the fact that we were working with a graduate student in their own respective lab, so we kind of had to work on his time and when he was able to kind of set up the Hawkinson bar to meet our own testing needs. So outcomes for this project, we were able to identify and implement a reliable and repeatable method for testing the physical survivability of BTech sensors. We were able to conduct this in a safe and controlled lab environment. We were also able to collect preliminary data for the failure analysis of the accelerometers, and we were able to identify potential relationships between our testing parameters that would be useful going forward in testing in the future. So for our budget, we were initially given a budget of $5,000. This is because at first the project was more of we were supposed to build a machine from scratch that would be able to test these sensors. However, after our research, we determined that it would be better to adapt an existing method to meet our testing needs. So we only spent about $362, as you can see on the chart on the right. Only 57% of that was for those adaptations. So all the steel that we had to order a machine to adapt the Hawkinson bar. So we were able to save 93% of our initial budget. So for the timeline of the project, in the fall semester, the first couple of weeks were mostly just introducing the project, getting accustomed to what we were going to be looking at going forward. And then our research kind of carried us through the rest of the semester, looking at the different impact testing methods, looking at different ways Hawkinson bars have been implemented in the past. And that continued forward into the spring semester, so we ordered all our parts, got those parts machined, and then we were start testing that carried us through the rest of the semester, analyzing the data from the tests, and working with our client to optimize our testing procedures. So going forward, our client wants to continue the failure analysis of the sensors, looking at the impedance data in between tests. They want a functioning model on the computer in console, so they want to be able to look at finite element analysis to find when these sensors will fail and load. And they also were talking about a potential adjusted size adapter so that for each test there's a consistent centering of the sample so that there's not variation in between each test for the analysis of the data that we're looking at. And thank you. Any questions?